No, it's Mrs. Ionic. Okay, so we are going to talk about two other parts of this triangle today.
Oh, is he recording?
So, this is kind of cool because there's actually three types of bonding that we're going to talk about in this unit. We talked about covalent, where they're completely sharing the electron, okay? But we know that covalent bonds all have some ionic character, right? So we have polar covalent here, polar bonds but still sharing, and then eventually we move to ionic bonds. Okay, but what if both of the things we're talking about are on the left of the periodic table? We're talking about two metals bonding. They're going to have similar electronegativities. Turns out we're going to have to use a slightly different way to think about how metals bond with other metals. Okay, so 2C.2 and 2C.3 is what I want to try to get into today. 2C.2. Osama, read it for me.
That's a mighty fine request.
Yeah, I was meant to shame you in figuring out where your outline is.
Oh, it's somewhere downstairs.
Yeah, by my bathroom pass?
No, it's in my locker. It's in like my pile.
All right, read.
All right. Ionic bonding results in the net attraction between a positively charged ions closely packed together in a crystal lattice.
Crystal lattice. Who's heard that word?
Oh, you gotta emphasize just how real it is.
All right. Crystal lattice. Here's like the poster child for crystal lattices. Poster child. Sodium chloride, NaCl, right? However, there are all kinds of different crystal lattices. There's some complicated ones. There's some not so complicated ones. Osama's got some on his poster. Ooh, there's a good one there.
Poster, by the way, it's a patent.
I can buy me research paper.
I made sure to follow Nasba's tradition and make the logo very
What research
Osama does, but he's not even listening to me very rudely. So he's not even getting that. I'm sort of trying to compliment him for once.
Dang.
Whoa. So there's an example of a crystal lattice, although this looks a lot different than the one that I just showed you.
That's beautiful.
Because one way of showing crystal lattices is to show the smallest bit of that crystal lattice that still contains all of the parts. That's what I mean by that. What I mean is, if this is the smallest unit, I should be able to use it as like a stamp and basically stamp these atoms in all directions, and it should look like the substance does on an atomic scale. Okay, this is called a unit cell. This is the smallest bit of a ionic substance that still has the correct ratio of all those ions.
Just a question.
Yeah.
Would that happen to be a peroxide?
It might be.
So you're like tessellating that.
It's like a tessellation, yeah, in geometry. Tessellation is some pattern that you can just repeat over and over and over again, and it fills all the space, right? Unit cells are atomic tessellations, actually ionic tessellations, something that you can repeat over and over and over again, and it'll show you what the whole thing looks like. Okay. There's some pretty cool stuff in here that we're not going to get into anymore. But I made this thing a few years ago.
It's beautiful.
Yes, because if you think about atoms and how they're going to fit in with each other, right, it makes sense that if three atoms come close together, there's going to be a little dimple in the middle of those, and another atom would sit right on the top of that dimple, right?
Yeah.
Okay, so these are all filled in that way, that the atom is filling in the dimples of the atoms in the layer below it.
If you didn't use like solid layers, you could show it.
Within that
I got my time so bad.
is this little sort of crystal lattice thing here. This is the smallest unit that if I repeat this thing over and over and over again, it looks like the way these tennis balls
Wait,
are.
so that would look like that?
Chop up the atoms.
This whole box is the unit cell. So the green and the blue represent these different layers. There's a couple different ways of looking at the way these things are arranged. Okay, but the unit cell for this material is technically sort of at an angle from the way we would think about them being stacked. Okay? But if I take this unit cell, I could repeat it over and over and over again and make this structure as big as I want, and it would represent the bonding. Okay, what's nice about unit cells is if you show them this way, you can figure out how many atoms are in this thing. Because there are some atoms that I had to cut in half on the faces, which means how much of the atom is in the unit cell? Half of it, right? I had to cut it in half, because only half of it is in this unit cell. The ones on the corners,
They're an 8.
1/8.
Yeah.
I had to cut them in eighths, and 1/8 of an atom is at each corner. Now, this one does not have any atoms on the inside like this one does here. This atom is completely inside of this crystal lattice. But what you can do is you can count up how many atoms are in here. 8 corners times 1/8 is 1 atom. 1, 2, 3, 4, 5, 6 faces times half an atom. 3. 3 plus 1, there's 4 atoms in this unit cell. If I knew the radius of one of these atoms, I could calculate the volume of this unit cell. If I knew the mass of this type of atom, whatever it was, I could figure out the mass of atoms in this unit cell, and I can actually calculate its density, which is pretty cool. All right, we're not going to do that because they sort of cut that stuff out of here, but we do have to understand what a unit cell, or what a crystal lattice is. Closely packed together in a crystal lattice. So this is just a unit cell. This does not show you the entire lattice, just the smallest part of that lattice that has all the pieces in it. This might be a slightly larger version of that, right? Showing how many does this have? It looks like it has 1, 2, 3, 4, 5, 6, 7, 8 of those unit cells we just saw, now all connected to each other, right? And so this is showing a larger picture of the crystal lattice. Okay. How'd I get 8? Because the other crystal, the unit cell only had one of those titaniums. I think these are the titaniums. So there's 8 titaniums in here, so I know it's 8 of those unit cells. But really, the key features of the crystal lattice that we need to understand can be shown here. What are the key features?
Blue and green.
Well, read part A for me, Deborah.
Anions and ionic crystal are arranged periodic 3D array that maximizes the attractive forces among cations and while minimizing the repulsive.
So how is this picture maximizing the attractive forces among cations and anions?
It's not putting like the cations next to each other because that would be repulsive.
Yes, if you look at any particular cation, which ones are the cations?
One.
Green one.
Green one. Blue one.
Green one.
2 choices. Both. This will be on the test tomorrow.
It's the blue ones.
What?
It's the small one.
Which ones are the cations and which ones are the anions?
Blue ones.
Blue.
The small ones are the cations. Why?
Because they kind of lose like
Because the plus
electrons
charge.
and lose a shell.
When we pull a shell, when we take a shell off of an atom, it's like peeling an onion. What's left has to be smaller than what we started with, right? If we're losing an entire shell like we do with cations, the resulting ion must be larger, or sorry, smaller.
Oh, self-harm.
It's called negative reinforcement. Okay.
That's not negative.
The green ones are anions. Why are anions bigger than their neutral atoms?
Because they have more electrons.
They add more electrons to the same shell. More electrons in any shell are going to lead to electron-electron repulsion, making that shell bigger. Okay? So if you notice, any particular anion is entirely surrounded by cations. Well, there's also a green here, but notice the green, there's a little bit of space here. So the greens are as far away as they can be, but they're as close as they can be to the blues. So they're maximizing the attraction between the oppositely charged ones and trying to minimize the repulsion. Look at how far apart these blues are. That's going to minimize the repulsion that blues are going to experience with each other. Michael?
Well, what if you have something like potassium chloride or something like that, where they'd be
Isoelectronic?
Yeah, isoelectronic.
Isoelectronic. They have the same configuration of electrons.
Yeah, would you just say that the potassium would be smaller because there's more?
Higher zap.
Yeah.
Yeah, 'cause there's more.
Yeah. So remember, we have to be able to compare neutral atoms to their ions, but also have to be able to compare species that have the same electron configuration but different numbers of protons. So if they have the same electron configuration, the one with the more protons is going to be smaller. Okay. That's not the same explanation for why cations in general are smaller, because potassium and potassium plus both have the same number of protons, right? So in that case, to explain why potassium plus is smaller, you can't say, oh, it's got more protons. What? They're both potassium, right? You have to say it's removed an entire shell of electrons, specifically the 4s, and so what's left is going to have to be smaller. Okay? All right, so we are maximizing attraction and we're minimizing repulsion. What else? It says it's systematic and periodic. Right? Periodic means repeatability, like we talked about with unit cells. I can repeat this pattern as large as I want, and it's still going to retain those properties. Maximizing attraction, minimizing repulsion. It's also three-dimensional. Will you be asked to represent three-dimensionally? I hope not. That'd be really hard. So we're typically going to show them in 2 dimensions, but the same kind of rules apply. Okay? Woo! Part B. My 4th best friend again. Jack.
Coulomb's law describes the force of attraction between the cations and anions in the ionic system.
So Coulomb's law applies. You knew it was going to, right?
Yep.
Yes. So, how does Coulomb's law apply to crystal lattices? What's Coulomb's law again?
KU1, Q2.
Oh, well, that's for point charges.
So in the crystal lattice, what are we talking about with R squared?
Distance between.
Distance between them. Okay. Now what's Q?
Constant.
Charges.
Oh, your Q.
So we have positive charges and negative charges, right?
Oh.
So what are we going to have to do? What we're really going to have to do is compare different ionic compounds and say which ones are held together more strongly. So for example, if I gave you lithium fluoride, actually, if I gave you sodium chloride versus magnesium sulfide,
Oh.
is there a way for you to predict, using Coulomb's law, which one is going to be held together more tightly?
Yeah.
Yes.
Yeah, what? Michael?
You say the in magnesium sulfide, they're each like +2, -2, and that's the charges.
So Coulomb's law tells us the bigger the charges there are, the more the attraction, right? That's how we explain some of the left to right trends. As Zeph increased, the force of attraction increased. Okay, but here we're talking about the overall charge on the ion. So if the charges are greater, but the ions are similarly sized, I'm going to say the bigger charges are going to be more attractive. Right? We can also make some predictions based on the size of the ion. So I could compare NaCl to RBI. Rubidium iodide. Not as bad.
Yeah.
Yeah. comes on the brain or what?
Not a question.
Yeah.
Dude. Whoa, whoa, whoa. So you only see color?
Who's going to be held together more tightly?
NaCl.
NaCl. Why?
Because the R-squared value is greater.
Cause it's small.
Because they're smaller. The smaller they are, the closer those ions are together. So I drew a picture. Yeah. This would be like NaCl here versus rubidium iodide here. Bigger ions, the distance between the ions is going to be larger. Coulomb's law says when the distance is larger, the force is weaker. So if we're describing something like melting point of these two, which is really kind of a measure of how much it takes to sort of move those ions relative to each other, sodium chloride should be higher. Smaller ions, closer together, bigger force. Okay. Then over here we have magnesium sulfide versus sodium chloride. And so in this case we're talking about the magnitude of the ionic charge. Similarly sized ions, but having bigger charges means a bigger attraction. Okay. All right. And I believe that's what it talks about in part 1 and 2 under B. Coulomb's law describes the force of attraction between cations and anions in a crystal. Yep, larger charges, stronger attraction. Smaller ions, stronger attractions. Okay. Learning objective 2.19. Lily.
Where is that?
The bottom of the page.
Very end of 2C.2.
Oh. The student can create visual representations of ionic substances that connect the microscopic structure to macroscopic properties and or use representations to connect the microscopic structure to macroscopic properties.
Okay, so we have to be able to draw little pictures of ionic substances like this. We have to be able to draw little two-dimensional crystal lattices in order to explain certain properties. What are those properties? Boiling point, okay? So they might ask you to draw a picture showing why the boiling point of NaCl is higher than the boiling point of rubidium iodide. And so you would show the rubidium iodide ions as being larger, and you might have to explain it using Coulomb's law. Yeah?
Yes.
Okay, so... Thought. Solubility we're not going to talk about just yet.
Hardness.
Because solubility makes up a big portion of enduring understanding 2A. 2A3 says solutions are homogeneous mixtures in which the properties are dependent on the strengths of interactions among the particles. So we're going to draw the pictures to represent solubility in 2A3. Okay, so we'll come back to that. Hardness and brittleness. Hope, what you know about brittleness? It's not on there, so don't look.
Oh.
Talking about accessing background knowledge, Hope.
I know it's soft.
It's what?
Soft. It breaks easily. It's not soft. Breaks easily, yeah. Not necessarily soft.
Well, actually, softness and hardness are different than malleability and non-malleability. Malleability and brittleness, right? You can have something that is relatively soft. But yes, it could be relatively soft, but you can bend it and move it, right? You could have something else that's relatively soft that, well, yeah, I guess they're pretty closely related. Okay. I'm trying to think of an example of something's hard,
Myra.
Yes.
but not brittle.
No.
Well, brittleness doesn't just mean you look at it and it breaks.
Wait, really?
Okay? But the example I used in the last class for brittleness would be dropping things off of your dinner table.
Why?
Because you're a klutz.
I am.
Yeah.
I really am.
Because it's things that people probably have some familiarity with. Okay? Which thing on your dinner table is going to break?
A plate, a cup, a
Plates,
spoon.
glasses, a spoon. So yes, we can actually explain the brittleness part of it by thinking about why does a plate break when we drop it on the ground? Has anybody ever dropped a plate on the ground and it didn't break?
Yes. Actually.
You got lucky.
Fun
You
stuff.
betcha.
Okay, so we have to be able to explain why sometimes when we drop a plate, or like somebody, I think it was last year, dropped a beaker from this high and it did not break.
It's called luck. It's
Bounce.
called
Was it
luck.
Dijon?
Madness.
Honestly.
I just heard it like ting, 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 ting. I was like, what the heck was that? They're like, oh my god, it was a beaker! It didn't break, right? And then some unlucky punk always like sets it down from like right here and
That
it
was
shatters.
last year.
I broke 3 last year.
Everyone kept breaking
I
testers.
broke 2 on the first date.
Malleability is the opposite of brittleness, really. Malleability is like the ability to bend something, to pull it into wires, maybe. Bend it. Pull it into wires, yes. Most metals are very malleable. You can bend them, you can shape them, you can stretch them out, and they don't break. Okay, but ionic substances are not. That's why it says lack of malleability. Why can't we bend them, stretch them, do whatever we want? Rochelle,
Can we get a break?
can we get a break when I'm done with my thought? No, you can't run out with all those maniacs that are screaming out in the hallway right now.
Especially like,
I just need a break right now.
It's gonna make you guys dumber.
Can't get worse.
Okay, so let me explain why when you drop that plate on the ground, it shatters. Because
Mr. Bull, I can't see the board.
you can't see the board.
Yeah,
Why not?
like, because you're standing in front of it.
Then he's gonna stand in my way.
No, no, the other one.
Okay, so there are certain ways that we might hit this crystal and break it. Specifically, I can think, or I can see of one right here. If I hit this thing right here, what's going to happen? That corner is going to move. And what will the lattice look like after that?
Weird.
Well, here's the part that I didn't move.
Oh, it's gonna repel.
If I move this little corner of 4 atoms up,
This is magic.
I might move it to that position there. Yes, now instead of having oppositely charged ions next to each other, now we've moved it so that there are similarly charged ions next to each other. And instead of attracting, now we're going to repel.
Okay.
So they're going to repel and that thing's going to break. We haven't maximized the attraction and minimized the repulsion. We've maximized the repulsion and minimized the attraction. So now that thing's going to break. Okay? But if I hit it in just this another way, I might not cause that same shift where negatives line up with negatives and positives line up with positives. Okay? In reality, most ceramics and most glasses are much more complicated. They're not perfect, perfectly arranged like this. We're going to learn about that in 2A. But this is sort of the idea. Please take a break, guys.
Bless your soul.